Hello everyone, this video covers section 3.4, Hermite polynomials. Before we go to this section, let me just remind you or refresh your memory of what we have done so far. So far we have Lagrange polynomials, which are going to be essential to many things we're going to do later. We also did Navier method. And in section 3.3, we talk about Newton's divided differences. And remember, the differences could be also called forward difference or backward difference if you use equally spaced x values. By the way, there is also center differences, which I didn't go over, so therefore you don't have to worry about it. In this section, we're going to do some very specific or special polynomials called Hermite polynomials. These are actually part of a bigger class of polynomials called oscillating polynomials. And oscillator means, I think, kissing, and you'll see how it's relevant in a little bit. But oscillator polynomials have two features. The first is not new, is the polynomial agrees with f at the points x0, x1, all the way to xn. So this is not new. This was the conditions required in the previous methods. The second condition is what makes this different, and the oscillator polynomials also agree with f prime. So therefore, not only the function agrees with f prime, but also the derivative at the points x0 all the way to xn. So therefore, because of these two things, that implies that the polynomial and the function have the same shape. It doesn't mean they are the same, but they are closer than the previous sections. Now, in reality, it may be very hard to know what the derivative values are. So therefore, this is not very practical if we don't have these values. But if you do, then like you will see right now, the approximations are pretty good. All right, so let's look to the formal definition of Hermite polynomials. So if f is a continuous function, where the first derivative is continuous, and then x0 to xn belong to a and b, then the unique polynomial of least degree, okay, agreeing with f and f prime, is called the Hermite polynomial, with degree at the most to n plus 1. So again, since they had to agree at the points x0, x1, x2, and so forth, and also the derivative, this is what we mean by the same shape. Let's say this is x0, x1, x2, and let's say that the function f looks like this. So this will be f of x. And then since the function agrees with the derivative, so therefore p of x has to have the same slope. It doesn't necessarily will be the same function, but it will be closer. So p of x could look like this. So you can see it will be closer. Well, in this case, it will be called h of x. Now here are the bad news. The polynomial is gonna look like this. So this will be the part where it matches the function, and this is the part that matches the derivative, where this is equal to this beautiful thing, and this is equal to this part. here L prime means derivative, just like before, and L and J are Lagrange polynomials, the ones we did before in section 3.1. So this is not hard, but it's going to be a lot of tedious work. All right, so let's do an example and see how this works. Like I just mentioned, this is not hard, but it's going to be pretty tedious. Now in section 3.1, we use this information and we come out with Lagrange polynomials at that time. So from section 3.1, so you should check this. We get this L to 0 was equals to 2/3 x minus 2.75 times x minus 4, which if we simplify, this will be 2/3 x squared minus 9/2 x plus 22/3. Now you can use decimals too. I just leave it in like this so it's more accurate. Then L to 1 was equals to minus 16/15 times x minus 2 is x minus 4. The only reason why I rewrite it is so that it's easier to take the derivatives. So therefore it's not required as long as you take the derivative correctly. So then this is equals to minus 16/15 x squared plus 32/5x minus 128/15. And then finally L to 2 is equals to, or was equals to 2/5 times x minus 2 times x minus 11/4, which is, this is 2.75, and then this simplifies to 2/5 x squared minus 19/10x plus 11/5. All right, so therefore from here the derivative L to 0 prime is going to be 4/3x minus 9/2. From here, the derivative of L to 1 is going to be minus 32/15 x plus 32/5. And the derivative of the last one is equals to 4/5 x minus 19/10. All right, so next we need to find h and j and h and j hat. So let's start with the first one. So here the value for n is equals to 2. So n is equals to 2. So let's start with H2O. Let's start with water. This is equals to 1 minus 2 x minus x 0 times L prime of 2 0 of x 0 times L to 0 of x 0, the whole thing squared. Actually this is just x, not x 0, which if we plug in the values, this is equals to 1 minus 2 times x minus x 0, which is 2, times L to 0 prime of 2 times L to 0 prime, which in this case this is going to be 2/3 x squared minus 9/2 x plus 22/3 the whole thing squared. All right, so now notice the L2, you find L2 prime 0 evaluated at the point 2, that this is equals to negative 1.8333. So you should check on this. So then this is going to be, if you plug it in, this will be 1 minus 2x minus 2 times negative 1.83333, and then this one stays the same. And once you simplify everything, this will give you 3.66667x minus 6.3333 times the Lagrange polynomial square. Now, just like in the previous sections, we will be interested for this particular case to find how much is h20 evaluated at 3. And therefore, you're going to plug in 3 in here, 3 in here, and so forth. And you should check that all of this is actually equals to 4.6668 times 0.2777a, and this is equals to 0.12963. Okay, so definitely check this, because this is the value we're going to use in a little bit. All right, so now we need to find h20 hat. All right, so h20 hat, by definition, is going to be equals to x minus x0 times ln 0x squared. So in our case, this will be x minus 2 times 2 over 3x squared minus 9 over 2x plus 22 over 3 squared. Therefore, from here, if we evaluate this function or this polynomial at the value of x equals to 3, this will give you 0.02777a. And again, just check all of these values. So stop the video if needed and check that you get that. So now to do the rest is going to be exactly the same. So therefore, to find h21, this is going to be now 1 minus 2x minus x1, but x1 is 2.75, times the derivative of L21 evaluated at 2.75, which is actually 0.53333. So again, you should check that. Then we have this L21 prime evaluated at 2.75. This is equals to 0.53333. So you should check all of these ones too. And then times the polynomial, which will be minus 16 over 15x squared plus 32 over 5x minus 128 over 15 and everything squared. Right, so therefore from here we have the h21 evaluated at 3. If you plug in the value for 3 in here, and simplify, you'll end up with 0.73332 for the first part times 1.06667 squared, and this is equals to 0.83 436. Right, so therefore h21 hat is going to be equals to x minus 2.75 times minus 16 over 15 x squared plus 32 over 5 x minus 128 over 15 and the whole thing square. Which from here, if you evaluate this at the point 3, this will give you 0.28445. Again, just check these values. Like I said a few times already, this is not hard, it's just tedious, especially because you have to be very careful doing arithmetic. So you make a small mistake, you have to start over, and that's why we're using MATLAB to do long problems of this kind. And you just have to be very, very careful. So not everything in life is fun. Sometimes you have to suffer a little bit, but this will build character and patience in you, which will be very useful in your life. Anyways, let's go to the last two. So we need h22. By definition, again, this will be 1 minus 2x minus 4, which is x2, times 1.3. 1.3, it will be L22 prime if you evaluate it at the point 3. This will give you 1.3, so you should check that, times 2 over 5 x squared minus 19 over 10 x plus 11 over 5 square. So again, this value comes from here. Now h22 simplifies to 11.4 minus 2.6 x times the polynomial square, and you should check that from here h22 of 3 is equals to actually 0.03600. And then the last one, h22 hat, is equals to x minus 4 times the polynomial, which is 2 over 5 x squared minus 19 over 10 x plus 11 over 5 squared. And from here, h22 hat evaluated at 3 is equals to minus 0.01. Okay. Now, since the value for n is equals to 2, that implies that we're finding h5. And by the definition, this is equals to the sum from j equals to 0 to 2 of f of x j hn j of x plus the sum from j equals to 0 to 2 of f prime of x j times h hat n j evaluated at x. So in our case, this is equals to f of x 0 times h to 0x plus f prime of x 0 times h to 0 hat of x plus f of x 1 h to 1 of x plus f prime of x 1 h to 1 hat of x, and then plus f of x 2 h to 2 of x plus f prime of x 2 h2 hat of 2 of x. Alright, so remember that we are using this information x, f of x, where f of x is just 1 over x. Remember the values we used were 2, 2.75, and 4. And then the values for x, this one was 0.5, 0.36, 36, 3, and this one was 0.25. But now we need to have the derivative also, which is easier to find for this case. Remember the derivative is minus 1 over x squared. So the values will be minus 0.25, minus 0.13223, and minus 0.0625. So remember that the main disadvantage of this method is that it requires that you have the values of the derivative, which you may not have at all, or the function may not even be continuous. Okay, so this is a huge requirement that could not be met. All right, so now we have all the information to build this Hermite polynomial. So we know these are the values here. We just calculated these values in the previous in this page. So let's use this polynomial to approximate. So let's approximate, let's say again f of 3, which we know is equals to 1 over 3, which is 0.33333, which is what we have done a few times. So therefore, if we use the Hermite polynomials, we will get the following. So from here, we will have h5 of 3, it will be equals to 0.5, which is f of x 0, times h of 0, which will be 0.12963, plus minus 0.25, which is the value of the derivative, times 0.027778. So this is equals to this part, and then plus 0.363 times 0.83436 plus minus 0.13223 times 0.28445, and now this part is representing this part, then plus 0.25 times 0.036 plus minus 0.0625 times negative 0.01, where now this represents this part, and then if you simplify everything, you will get 0.3332a, which you can see is very close to the actual solution, which is this one. So this is actually the closest we've been to in all the approximations we've done before. But as you can see, this takes a lot more work. So the main disadvantage of this method is that it's too long, it requires too many computations. The other disadvantage is that it requires that you need to have the derivatives, which you may not have. And the advantage is that it's more accurate, but you have to do a lot more work. Now you can also mix or combine Hermite polynomials with divided differences, but you don't have to worry about that. All you need to know is how to find a Hermite polynomial exactly the way I did here. All right, so that's it for section 3.4.